Okay. So, last details in section 4.1. And that was all about inverses. This was the stuff we did last time. And ideally, if I had 5 extra minutes at the end of class last time, I would have done this last time, but I didn't, so here we go. F of x equals x squared is a function, but not one, oops, put my hyphen in the wrong place, but not one-to-one. And the quickest way to explain to someone why this is not a one-to-one function is by showing them the graph and showing them the graph fails the horizontal line test. So therefore, it is not a one-to-one function. Okay, we were sort of talking about this at the end of class last time. The thing that I was mentioning at the very end of class, just so you remember, is that f of x equals x squared is not the inverse of the square root of x. Those are not inverses of each other because they're different. They don't have the reflection. They don't have the same order pairs that swap. The domain and range don't swap, so they're not inverses of each other. And that was our very last detail from last time. But here's something we can do, everyone. We can do this. When I present a function, I can adjust the domain. I can say something like this, everyone. I want to look at the function x squared, but I'm going to make a rule that I'm only going to plug values in there that are greater than or equal to 0. That's my rule, because I'm the one who's working with this function right now, and I'm allowed to say that. So I'm going to tell all of you, for right now, this is going to be the function you think it is, but I only want to look at the positive values. In other words, I just want to look at the domain from 0 to infinity. And if I do that, then the graph will look like this. So I can artificially restrict the domain if that's the equation I want to look at. I can say, hey everyone, it's still going to be the x squared function, but I've decided we're not going to plug negative numbers into that today. And now, is it a one-to-one function? Yes. This is a one-to-one function, and its inverse is the square root of x. Because the square root of x, everyone, is going to be a reflection over the line y equals x. If I draw this again, I can say here is h of x equals x squared with the condition that I'm only going to put positive numbers or 0 into that. And then right here is h inverse of x equals the square root of x, a reflection over the line y equals x. So you can take a function that's not one-to-one and look at just a piece of it and have a one-to-one function. That's the goal here. So we can take a function that is normally not one-to-one and just look at a piece of it by restricting the domain to get a one-to-one function. So if you ever see a function, it is possible the person that writes down that function might put something next to it and say, we're just going to look at a piece of it. And this is what it would look like. They would say this, and then next to it they would say something like this. And what that does is it restricts the domain. So now we know that. Now, if I just write x squared up there, you have to assume it has its normal domain. But as soon as I restrict the domain, I have to make that very clear that I'm doing that. That's my job. So I'm not allowed to just say from now on x squared is 1 to 1, because it's not 1 to 1. It clearly isn't 1 to 1. But if I go out of my way to tell you just this piece of it, then yes, I can make it 1 to 1. Everyone okay with that? You might see that come up in your homework. This might save you a few minutes this weekend. If you decide to start working on the 4.1 homework this weekend, and I hope you do, if you haven't already, then this right here might save you a few minutes. If you already did the homework, you know exactly why that would save you a few minutes. If you haven't done the homework, you will see later why that will save you a little bit of time. I think it's actually the last problem it helps you with. A little present for everyone there. Okay, and that's going to be the end of section 4.1. Any questions, comments, complaints? All right. So this is a fresh unit, which means we're going to talk about a fresh, different type of function, exponential functions. Now I need to make a couple things very clear about exponential functions. They share some vocabulary with polynomials and rational functions, but do not follow the same rules. In other words, class, you're going to hear me use the word asymptote. You're going to hear me use the word intersect. You're going to hear me use domain and range. And while we know what those words mean, basically, I don't want you to try and apply the rules from other functions that we've already learned about to these new types of functions, because they follow a whole new set of rules. So don't apply old rules, something like, I'll give you an example, like end behavior, or asymptotes to exponential functions. Because you're going to go crazy if you try to do that, because they just don't follow the same set of rules. They're a brand new type of equation, a brand new type of function. All right. This is what they look like. Just so you know, the letter you use kind of down there is arbitrary. Some people are going to say a to the x. I like to use the term b to the x. And the reason I like to use the term b to the x is because we're going to call this the base of the exponential function. And b, base starts with b, so I think that makes more sense. But if you're reading about these later and you're seeing all these rules or something like that, and they're using the term a to the x, it means the same thing. So don't let that throw you. I know little details like that can throw you. This is what an exponential function looks like. Examples would be things like this. G of x equals 3 to the x. H of x equals 5 to the x. P of x equals 1/2 to the x. What we have here, everyone, is we have a number as a base, and we have the variable in the exponent. We have a number as the base and a variable as the exponent. And the reason I make such a big deal about this is because this is brand new to us, everyone. Because when we had polynomials and rational functions, a polynomial had the variable down below kind of as the base, and it had a number up there as the exponent. That was one of our polynomials. But the exponentials, the things we're going to be talking about today, are quite the opposite. They have the number down below, and they have the x, the variable, up in the power. So it is a brand new type of function, follows a brand new type of rules. The base of an exponential function, and everyone, just so I don't confuse you, I apologize for this. Saying exponential function is the same as saying exponentials, just like saying polynomial function is the same as saying polynomials. Same thing. So the base of an exponential function, or exponentials in general, must be any positive number except 1. So when we write these things, what we're going to do is we're going to write a number down below, and we're going to write an x up in the power. And that number down below must be a positive number, but it cannot be the number 1. Any other number will work. Fractions, decimals, whatever you want. Exponentials, unless the domain is restricted, can handle any value. In other words, the domain is going to be negative infinity to infinity for these unless someone comes along and does what I was doing before and said, nope, I'm just going to look at this piece of it. So we're going to have these functions, everyone, where we can plug anything we want into them. Anything we want into them. And the base can be any positive number except for 1. So, class, the first two there are exponential functions, because the base is a positive number not equal to 1. Fractions can be positive numbers. The last two are not exponential functions, because the base can't be a negative number, and the base can't be 1. So that's how we're going to decide if it's an exponential or not. So these are exponentials. These over here are not, because they break the rules. And we've had rules with functions before. We know that when we have like a polynomial, for instance, we knew this was not a polynomial because even though it sure looks like a polynomial when I first start writing it, we weren't allowed to have negative values in the powers, right, for a polynomial? So even though it sure looks like it was going to be a polynomial, this one's not a polynomial because of that right there. Just like those are not exponential because I'm not following the rules of exponentials. All right. So once upon a time, we made a brand new function called f of x equals x squared. And we decided to graph it by plotting some points. And when you plotted points for this thing, you picked x values and you plugged it in, and plugged them into the equation. And it didn't matter what x values you plugged in because the domain was anything you wanted. You were allowed to plug anything you wanted there and get a bunch of y values. Which table would you rather fill out, the first one or the second one? The first one. Because if we're going to get a bunch of ordered pairs, is there any reason to pick the most complicated numbers we can think of? No. Now, if your mathematical career depended on it, could you fill out this table on the right if you needed to, especially if you had a calculator? Absolutely, you could. But when we start out with a new function and domain is negative infinity to infinity, we should plug in easy x values. I'm not saying we can't plug in these, but I'm also saying there's no reason to plug in these. This right here hurts, but it is possible. And this one over here, I can do just like that. So why not pick the easy one to get started? All right, that being said, we need to know how to plug numbers into one of these things. So, there's the rules for the base, everyone. Whatever that base is, it needs to be a positive number, and it can't be equal to 1. And therefore, this is an exponential function. Some of you might already know this stuff, but it's never a bad idea to review this. So I apologize if some of you get bored by this next part of the lecture, but I think it is important that we're all on the same page. Everyone, what's b to the first power? B. It doesn't change at all. How about while we're doing this, we do the same thing over here with a number. 3 to the first power is 3. B squared is just b squared. But what would 3 squared be, everyone? 9, because it means 3 times 3, or 9. And b to the third is just b to the third, but that would be 3 cubed, or 3 times 3 times 3 equals 27. And pretty quickly we get to a point where we don't want to have to graph that, not because 27 is a difficult number, but because it's way too high on our y-axis. So let's try this. B to the 0th power. Does anyone know what that is? I'll give you a hint. It's not 0. It is 1. Very good. It's 1. Yeah, it turns out that anything to the 1 power is itself, and anything to the 0 power is 1. Those are two good rules you would do well to remember. Anything to the 1 power is itself. Anything to the 0 power is 1. All right. So just remember, I'm going to put some common mistakes over here. B to the 0 is not 0. Does anyone know what b to the negative 1 is?
1 over
3 to the negative 1, yes, is absolutely going to be 1/3. You're absolutely right over here. And therefore, this would be what?
1 over b.
1 over b. Well done. Yes. And what's the common mistake you think people think? A lot of people think b to the negative 1 is going to be negative b, but it's not. It's not. And for any negative power, put the base in the denominator and raise it to the positive power as usual. In other words, class, if someone gives you b to the negative 4, you just rewrite that as 1 over b to the 4th. You put it in the denominator, and then just raise it to the power as normal. So if someone gives me 3 to the negative 4, I just do 1 over 3 to the 4th. I do 3 times 3 times 3 times 3, and I get 1 over 81. So the negative powers don't need to be a mess. They don't need to be a nightmare. You just need to remember, it doesn't make the negative. In fact, taking a positive number and our base is always positive to any real power in Math 121, all our powers are real. That sounds like the tagline for a superhero movie. All our powers are real. All right, taking a positive number, and our base is always positive, to any real power, Math 121, all of our powers are real, gives a positive result. In other words, class, we're always going to get a positive answer with these, which means our range is always going to be 0 to infinity for these. You can put anything in you want, positive, negatives, but you can only get positive numbers out. The range is always positive. All right. Everyone, is that a quadratic?
No.
If you remember back then, it's a quadratic. X squared is a basic quadratic. There's a reason I'm doing this, don't worry. I always have a reason. Is that a quadratic? I'm not going to make you graph it, but is it a quadratic?
Yes.
Yes, it is. What's the lesson here? Well, functions can be described the same way even when some are simple and some are complicated. So the word quadratic works for both x squared and negative 3x squared minus 1.7x plus 29.1. They're both called quadratics. So exponentials or exponential functions might look as simple as 4 to the x, or maybe 3/7 to the x. Remember that base can be any positive number I want except for 1, and that includes fractions. But that's also an exponential. Even though it's got a -5 on it, it's still got the most key point to it. It's got an x up here in the power and a positive base. That's not 1. Do we still have an x up in the power, everyone?
Yeah.
And do we still have a number down below? Yep, that's an exponential also. How about this? I don't know, q of x equals 2.7182818 to the x. Is that still an exponential? You don't have to like it, but is it an exponential? Yeah, of course it is. And so is this right here. R of x equals 201 plus 0.04 over 12 to the 12x power. The most important thing is that base is still a positive number, not equal to 1, and the exponent, even though this one has a 12 in it now, still has an x up there. All of these are exponential functions, just some of them look much more complicated than others. So we need to remember that just like our friends the polynomials and the rational functions, while there are simple looking ones, there are also much more complicated looking ones, but they still fall into that category of being exponentials. So now, we'll graph them, see what they look like. We will graph them. F of x equals 3 to the x, g of x equals 1/3 to the x. These are two different exponential functions. And just like I said I was going to, I am not going to pick the world's worst numbers to plug in there, because why would I do that to myself? But I can plug in anything I want, so I should plug in both a sampling of negative numbers and positive numbers. So we're going to generate some ordered pairs for each of these, because that's how we draw a new graph for the first time, is we generate some ordered pairs and we connect the dots. Everyone, what is 3 to the 0? 1. Anything to the 0 is 1. What is 3 to the first? 3 itself. What is 3 squared? 9. If you do 3 to the negative 1, it's not negative 3. What is it? 1/3. And if you do 3 to the negative 2, that's just going to be 1/9. 1 over 3 squared, or 1/9. 5 ordered pairs, just like that. Anything to the 0th power is what, everyone? Anything to the 0th power. 1. Anything to the first power is itself. And anything to the negative 1 power is itself flipped. So, 0 power, you're going to get a 1. First power, you're going to get itself. Negative 1 power, you're going to get itself flipped. And we put a 2 in here, we square 1/3, we're going to get 1/9. We put a negative 2 in there, we're going to flip it and square it, and we're going to get 9. By the way, just so you don't make a false assumption about where I'm going with this, f of x and g of x are not inverses. I know we spent a lot of time on that word last time, inverses, and you might think that's where I'm going with this, but I'm not. They're not inverses. There's 2 exponential functions. Do you think 5 ordered pairs, is kind of a loaded question because I think it is, but do you think 5 ordered pairs is enough to start drawing a rough picture of the graph?
Yeah.
Yeah, we should be able to do this. So, check out this cleverness that I did today. Let's see if this works. Haha. Yes, my side-by-side graphs have arrived. Okay, so I just got to plot these points, and I just have to be careful here to make sure that I do the best I can with the fractions. But if I plot these points, let's see, 0, I'm going to have 1. At 1, I'm going to have 3. At 2, I'm going to have 9. And then at negative 1, I'm going to have 1/3, get kind of close there, and even closer there. Connect it with a smooth curve. Over here, at negative 2, 9, negative 1, 3, 0, 1, 1/3, 1/9. How many ordered pairs are on each one of these graphs, by the way? How many are on the whole graph? Infinitely many. I used 5 to help me draw it, but there's infinitely many on them. So, each graph has infinite ordered pairs. I used 5 to get the shape of the graph. All right, so we know enough about vocab to say a few things about these graphs. First of all, the way I drew them with the arrows, does it look like they do indeed go left and right forever? They do go left and right forever. That's why we can say for both of them, the domain is negative infinity to infinity. Anyone want to say anything else? What else does it look like here? Do you see anything? You want to make an observation? I'll make another observation. Y-intercept for both of them appears to be 0, 1. What do we call this when it gets really, really close to something as you go really far out? What do we call that? Yeah, that's a horizontal asymptote. No. They both have a horizontal asymptote of y equals 0. The reason I bring this up is because this is one of the first major differences I want you to notice between exponentials and our rational functions, is these only get close to the asymptote in one direction. That did not happen before. This is new. That's why I said we can't apply the rules of old to the rules of now. Because what we notice for this one is we notice as x approaches negative infinity, the function gets close to 0. What we notice for this one is as x approaches positive infinity, the function gets close to 0. So they behave differently with their asymptotes, but they have the same asymptote. The range for both of them is 0 to infinity. And the biggest fundamental difference between these two graphs right here is that this one is increasing and that this one is decreasing. Remember, increasing and decreasing, that's when you have to say you're going from left to right. That's left to right. No x-intercepts, no vertical asymptote. Yeah, it's a lot when you see these brand new functions for the first time. It is a lot. That's why I put it in your notes, and that's why I record it, so you can listen to it later and watch it later and look at this later. What we could do is we could almost call these kind of basic exponential functions. We've learned about basic functions before. These are kind of basic exponential functions. What I did was I took the liberty of doing 3 to the x and 1/3 to the x. And the reason I did that, class, is because the book does 2 to the x. There's a selection from your book where they graph one using 2 to the x. So a different one than I did, but very similar. And I didn't talk about that because I wanted to talk about ours, and I just wanted you to have these in your notes so they're all in one place for you. They do 1/2 to the x also. So kind of just 2 more examples there we get for free because the book had them in there. Here's one of the biggest things we notice though, everyone, and this is one of the big takeaways from this, is this. If you have an exponential function, your base is bigger than 1, the graph is going to roughly look like that. If your base is bigger than 1, your graph is roughly going to have that shape. The base must always be positive. So if your base is between 0 and 1, such as a fraction, then it's going to roughly have that shape. There's basically 2 shapes to exponential functions. Either the increasing one or the decreasing one. And it all depends on the size of your base. Some people don't pay close attention to this and they say, oh, so if the base is positive, it's one way, if the base is negative, it's another way. No, the base is never negative. It's if the base is bigger than 1 or between 0 and 1. So that's very, very important to pay close attention to that detail. And I'm not talking about positive and negative bases. I am talking about bases bigger than 1 and smaller than 1, but still positive. So when you're going back through later today, and you're looking at this, and you're looking at how we graph them by plotting some ordered pairs, and you're looking about all the information I put on here, also take a look at the ones the book did. 2 to the x, and 1/2 to the x, because they also each did one of each, where the base was bigger than 1 and where the base was between 0 and 1. More examples, the better. All right. Exponentials to other powers. Now, the domain is negative infinity to infinity. So, I usually plug -2, -1, 0, 1, 2 into an exponential to get 5 ordered pairs. But since domain is negative infinity to infinity, you can actually plug in any number. We've had that for a long time. With polynomials, we can plug in any number we want. We just avoided plugging in nasty decimals or fractions and large negative numbers, but we can really plug in anything we want. So we can take a positive number to any power. I'm going to write that. We can take any positive number to any power. And there's no big mystery why we don't use 1 as a base, everyone. The reason we don't use 1 as a base is because 1 to any power is still just 1. So it's not interesting at all. So that's why we don't ever say the base. It's not like it's forbidden. It's not like dividing by 0. It's not the most evil thing in the world. It's just the most boring thing ever. So when someone writes this, when someone writes y equals 1 to the x, what they're really writing is just y equals 1. And the function for y equals 1 just looks like that. So it's not one of our exponential graphs. Not illegal, just not helpful. All right. 3 to the 4th. We're allowed to do that, aren't we? Why wouldn't you do that when you're drawing a graph? Because it's 3 times 3 times 3 times 3 equals 81, and no one feels like drawing a coordinate system that goes up to 81. This one I already did. I think I already did this one earlier, but what would 3 to the -4th be? And I'll tell you, this is not a math problem as much as this isn't a number crunching problem, this is a concept question. If you know 3 to the 4th, you should also know 3 to the -4th.
1 over 81.
1 over 81, very good. If you know it to the positive power, you know it to the negative power because you just flip it over. What if you have like a more complicated base to the 1st power? Does that change what it is? No, it's still just 2/7. If you have 2/7 to the -2 power, oh, let's do the 2nd power first. Getting ahead of myself. The 2nd power, that would be 4/49. You have to square both the top and the bottom.
You apply it to both sides.
Apply it to both the top and the bottom, that's right. What would 2/7 to the -1 be?
You have to flip them.
Flip it over?
Yeah, 7 goes on top, 2 on bottom. 7 over 2.
7 over 2. Everyone okay with that? How about this one? 2/7 to the -2 power. What's that going to be?
49 over 4.
So fast. Get your answers in today. Good. 49 over 4. All right, a little more interesting, a little more interesting here. I get carried away with this stuff and my pages get way too long if I don't remember to go to the next page. What does 1/2 power mean, everyone? It means the square root. Very good. It actually means the same thing as this, but no one writes it like that because we just assume that's a square root if we don't write a number up there. And remember, this always means the principal root or the positive root, so that would just be 3. What does a 1/3 power mean? Cube root. All right. What does a 3/2 power mean?
The 3 goes into the 25 and inside the radical.
The square root. And then
I'm hearing a lot of wisdom out there. I'm hearing a lot of wisdom. How about this, everyone? Is this correct?
no. You have to put the 3 to the 25.
Yeah.
Oh, so you're saying I should do this?
Yeah, under the radical.
And you put the 2.
Well, you could put the 2 outside, but just the
Oh, yeah.
thing.
Someone help me out. Which one's correct?
First. All right.
I like that. Neither. I'm sick of it. No. What's the square root of 25, everyone?
120.
5. Now it's time for your answer. What's 5 cubed?
125.
125. Okay. Someone, you want to cube 25 on your calculator for me?
125.
15,625, I think, if you cube it. And now take the square root of that. What do you get? Yeah, it doesn't matter. You're both right. It doesn't matter which one you do. Pretty slick, right? So here's the idea, everyone. If you ever have your base to a power that's a fraction, like this, here's what you do. You can either raise it to that power and then do the mth root, or you can do the mth root and then raise it to that power. It doesn't make a difference what order you do it in. And now we'll remember that because we had a lively discussion about it. So yeah, this is important. This is an important thing for understanding this.
It's tricky.
By the way, if for some reason someone hits you with a negative n over m, it's exactly as we just saw, except everything's taking place in the bottom instead. All right. Everyone who's packing heat today, check out your calculator. I want to show you something. Most calculators, the way you're going to do this, everyone, most calculators, the way you're going to do this is you're going to type in the 25, then you're going to hit a caret button, and then in parentheses, you're going to put 3 divided by 2. And this should get you 125. Some calculators, what you'll have to do is you have to do 25, and you hit a button that looks like this, y to the x. Then you type in 1.5, because that's the same thing as 3/2, and you get 125. Really what it's doing is in either order, it's cubing it and taking the square root. This is something, of course, I can't go around and check everyone's calculator during class, but always during office hours and always after class, I'm happy to take a quick look at your calculator with you and let you know how to punch the things in, how to punch the numbers in. Are we allowed to do this? Can I put a horrible, nasty negative decimal as a power? Can the power be anything I want? Yeah. Now, technically what this is, everyone, this is technically 1 over 3 to the 87th power 100th root, because that's 87 over, that's 87 hundredths up there. But no one does that. What everyone does is they reach for their calculator and they do, in parentheses, negative 0.87. Be careful, class, because a lot of calculators, there is a negative button, which is kind of a very short-looking negative sign, and a minus button, which usually looks just a little bit longer, and you want this one right here when you're doing this. It's very, very frustrating when you're using a calculator for the first time. You keep on hitting that minus button. It's like, error. It's like, what do you mean, error? If you do this correctly on your calculator, you should get roughly 0.3845. If you don't get that, I'm happy to help you with that later. All right, that is going to be a great place to break. So as we come back here, I've added something to the board, a part of the lecture that I call the illusion of growth on a hand-drawn graph. And what I want to point out to you is that when I draw these graphs by hand, no matter how careful I might be, it sort of looks like the right-hand side of the x squared graph, our old quadratic, and the right side of our exponential 2 to the x look kind of similar. It looks like they're both going up very, very quickly. But what I want you to do is I want you to join me as we talk about what happens as we get just a little bit farther down the x-axis. In other words, as we go down the x-axis, what would happen, for instance, if I were to plug a 20 into both of these? That's not that far out. And I were to do 20 squared, or over here, if I plugged in a 20, I would get 2 to the 20th power. Well, this one I can actually do in my head. 20 squared, 20 times 20 is 400. So this would give me a 400, and that means if you go out, not an obscene amount, just go out 20 points on here, this graph's going to be all the way up at 400. Anyone packing heat today can tell me what 2 to the 20th is? Yeah, it is, isn't it? It's 1,048,576. So the point I'm trying to make is when I just draw a bunch of graphs by hand, or even when we just draw the part of the graph that we see on a computer program, we sometimes miss the point, and the point is this. Exponential functions grow a lot faster than polynomials. You go out to 20 on this one, you're up at 400. You go out to 20 on this one, you're already up over 1,000,000. So, very difficult to tell from just a crude drawing, but it turns out, for the most part, and I say for the most part because of course it makes a difference on how big your base is or how big your power is, but for the most part, exponentials with base greater than 1 grow much, much faster than polynomials. Isn't that wicked, how fast that gets big? That's why you hear people say something is growing exponentially. They mean it's growing very, very quickly. Things that grow exponentially grow very, very fast. All right, next. F of x equals 2 to the x, g of x equals 3 to the x, and h of x equals 4 to the x. All have similar graphs. They all basically look like this, everyone. They all basically look like that, whether it's 2 to the x, 3 to the x, or 4 to the x. However, the larger the base, in other words, as the base approaches infinity, the steeper the right half gets, and the flatter the left half gets. I want to be very clear on this because I don't want you to misunderstand what I'm trying to tell you today, and that is these all have very similar graphs, everyone, but they're not the exact same graph. They do have different ordered pairs. In fact, the only ordered pair they have in common, these only share one common ordered pair. Do you know what that ordered pair is?
0, 1.
Yeah, 0, 1. Well done. The rest of them are different. Because if you put a 2 in all these, squaring 2, squaring 3, and squaring 4 gives you 3 different answers. Agreed? You put a -1 in there, you're going to get 1/2, 1/3, and 1/4. They're going to give you different answers. The graphs are different, but they do look similar to each other. They do look similar to each other. So please don't think that they all have the exact same graph. But it is fair to say they all have graphs that are very close to each other. That's allowed. All right, so larger the base, the steeper the right half gets, and the flatter the left half gets. Good. All have similar graphs, but not identical. And the same thing goes for this, everyone. The same thing goes for this. P of x equals 1/2 to the x. Q of x equals 1/3 to the x. R of x equals 3/19 to the x. All have similar graphs because the base is such that it's between 0 and 1. These all roughly have graphs that look like this. All have 0, 1 in common. But that is it. It's the only ordered pair they all have in common. They all have a base that's between 0 and 1, so they all go down. And it turns out, as the base approaches 0, holy cow, what does that mean? As base approaches 0,
From the left.
careful. It's a plus sign, so it's...
Oh,
It's all right. As the base approaches 0 from the right, the left side gets steeper, and the right side gets flatter. So is it safe to say that we have two basic types of exponential functions, the ones that go uphill and the ones that go downhill? Yes, that's safe. But you can't just think that there's one of each. There's infinitely many of each, depending on what your base is. So, two basic types but infinite versions of each type depending on the base. That's all I want to make clear, was that, well, yes, 2 to the x and 3 to the x look very similar. 1/2 to the x and 1/3 to the x look very similar. They're not the exact same graphs. They're in the same family. They look very similar. If I was just drawing a rough sketch, you really couldn't tell which one I meant. But they are different. So why do I do this? Because, exponential functions can be transformed just like in Unit 1 and change some properties. Now, class, this is something that I could easily spend an entire class period on, and we'd all get really tired of it and bored of it with graphing and all this stuff, and it's a pain in the neck. So, there are video examples on YouTube with the link on D2L, videos that I made that show a lot more of what I'm going to do right now, but I do want to give you the basics, of course, in class. But this, as I said, this can get very, very tedious, and we could easily just spend days on this if we wanted to, but we're not going to. But here's the idea. Two to the x looks like that, roughly. That's the shape of 2 to the x. Do you know what that looks like? Yeah, down 3. Didn't that always mean down 3 when you subtracted off the end of the function? I think it did. And when you shift a graph, or you transform a graph, lots of things happen. For instance, now the horizontal asymptote is at y equals -3. We now have an x-intercept, which we didn't have before. We now have a range of -3 to infinity, which is different. We now have a y-intercept of 0, -2. A bunch of things happen when you transform them. It changes the rules. It's still an exponential. It's just a transformed exponential. By the way, a little note for everyone. We can't find the x-intercept yet. I actually will teach you how to do that later in chapter 4, but at this point, we actually don't know exactly where that x-intercept is. I will teach you. I'm not like saying, you'll have to wait for the next class. No, you'll just have to wait a little later in this class. So we can transform these things and we can change them slightly. We can do things to them. I could take one of these things and I could take like f of x equals 3 to the x. And I could do this. Does anyone know what that's going to do to the basic graph? Notice where I put the +2. Notice the difference between where I put that +2 and where I put this -3. When it's right up against the x, what does that make you think of? Take a guess.
Left.
Yeah, left, 2 units. Good. This one was down 3. This one is left 2. And that doesn't change as much as you might think. It kind of makes it take a little bit longer to get going. It does change our y-intercept. Our y-intercept, I'm sorry, I did that wrong. Wait, did I do that wrong? Let's see here. I think that's going to go left 2, so it's actually going to do this. I'm sorry. I did draw it wrong. I'm sorry, it's going to go like that. And the y-intercept now is going to be at 0, 9. Because the whole graph went to the left 2. But the horizontal asymptote didn't change. The range didn't change. There's still no x-intercept, but the graph did move 2 units to the left. The two main ones that we need to worry about, the two transformations that we need to worry about most in this class, are actually not the vertical shift or the horizontal shift. The two big ones for us are vertical stretching or shrinking and reflecting are the two most important for us. And don't worry, everyone, I do know how to count to 3. I'm just counting vertical stretching and shrinking as 1, and I'm counting reflecting as the other. These are actually the two biggest ones for us to worry about in this class. Whether or not we're going to vertically stretch or shrink one of these, or we're going to reflect them. Now this gets very, very tedious, everyone, because for the first time in a long time, we start using the dot to mean multiplication again, which has been a long time, but you will see this show up. That's the multiplication dot. That means multiply these together. Now here's the rough part of this, everyone. This absolutely, 100% does not mean this. And the reason it does not mean that is because you're not allowed to do multiplication before you do exponents. So this does mean 2 times 3 to the x. And what that means is you double all of your y values. So if we were to plug in -2, -1, 0, 1, and 2, I'd get 1/9, 1/3, 1, 3, and 9. Because that's how it happens when you take 3 to the -2, the -1, the 0, the 1, and the 2 power. But if someone drops that 2 in front, it's going to turn it into 2/9, 2/3, 2, 6, and 18. What that does is it stretches the entire graph out. It is 100% not allowed to do this, because this is a different function. You can tell. Because if I were to do 6 squared, that's 36. It's a different answer if you put a 2 in there. So this is how you stretch out a function. You could also shrink a function. If someone gave me like 1/2 times, I'll do 3 to the x again. That'll be much more clear. I mean, all math is important to everyone, but I do realize this part of the lecture does get a little tedious. If you put a 1/2 in there, what that does is it's going to cut every one of these in half. So this is going to become 1/18, 1/6, 1/2, 3 halves, 9 halves. 1/2, 3, 1/2 times 3 to the x does not equal 3 halves to the x. So we are allowed to stretch one of these out, just like we did before, or shrink one of these down by putting a number in front of the whole function. Where this really starts to bug people is when I write this for the first time. What kind of number did I say the base had to be?
Positive.
Positive number not equal to 1. So, let's take a look at this, everyone. One 1/25, 1/5, 1, 5, and 25. You are allowed to put a negative in front like that because that negative does not mean the base is a -5. What it means is you're multiplying the base by a -1. That's right, everyone. Think of Pemdas, which I never really cared for very much, but I'm going to talk about it right now. What does the E's stand for? Exponents. Good, Stephen. Exponents. What does the M stand for? Multiply. Which one comes first? Exponent. So the first thing you do when you see -5 to the x is you raise 5 to the x power. Then you hit it with a -1. So this will be the thing that you're not allowed to do, just so we're clear, the thing that you cannot do is this. Because what does the P stand for, everyone? Parentheses. Which means it is -5, you're taking to the power of 0. That's not okay. This right here is an unlawful base of -5. Therefore, this is not an exponential. By the way, there's nothing wrong in mathematics about taking -5 to certain powers. What's -5 squared, everyone? It's 25. You can still take it to the power. It's just not an exponential function. So just don't misunderstand what I mean by this. Negative 5 can still be raised to different powers. It just can't be the base in an exponential function. Negative 5 can still be raised to certain powers. I can still do negative 5 to the third, negative 5 times negative 5 times negative 5. That's fine. I can still take the cube root of negative 5. But because it's a negative number, you can't take it to any power you want. So therefore, it cannot be a base in an exponential function. So whenever you see this, don't freak out and say, Steve suddenly broke the rules. What Steve's actually doing, when he writes that, is I am writing, if I write negative 3 to the x, I am writing negative 1 times 3 to the x. Parentheses make a difference. By the way, if you do choose to write one of these functions with a negative in front of it, like negative 2 to the x, what it will do is it will take the entire graph and it will flip it down over the x-axis like that. If you choose to write something like negative 1/3 to the x, notice that the negative's on the outside. It will take the entire graph and flip it over the axis.
So then it'd be impossible to reflect over the x-axis.
Oh no, you can reflect over the y-axis. This is
Oh,
the
yeah, the
x-axis I'm
y-axis.
reflecting over here, yeah, because the original, I know what you meant. The original one was up here like this, and the original one was up here like this. Thank you. No, you can do that. Let's talk about that for a moment here. All right, but I'm going to answer your question. But first of all, does everyone see what's going on here? How you can reflect it over the x-axis by dropping a negative in front? You're not making the base negative. You're putting a negative 1 in front of the whole thing. You're multiplying by negative 1. This is actually pretty cool. F of x equals 2 to the x. Looks like this. 2 to the negative x. Looks like that. It reflects it over the y-axis like that. 2 to the negative x is the same thing as 2 to the negative 1 times x power. Negative x is the same as negative 1 times x. That is the same thing as 2 to the negative 1 to the x power. What's 2 to the negative 1, everyone? 1/2. 2 to the negative x is the exact same thing as 1/2 to the x. Three halves to the negative x power is the same thing as 2/3 to the x power. 1/10 to the negative x power is the same thing as 10 to the x power. All right. All right, now I get to do something fun. Now we'll do something fun, everyone. Well, mathematically fun. How far do the numbers go? The digits go to the right of the decimal point for a pi. How far do they go? Infinitely many. Forever and ever and ever. So digits to right of decimal go forever. All right. What other numbers are irrational? Well, it turns out any square root that you can't completely simplify is irrational. So square root of 2, square root of 3, square root of 5, square root of 11, those are all irrational also. The decimal goes on forever and ever and never repeats. The reason you never see anyone use e as a variable in a math problem, lowercase e, is because lowercase e is actually also an irrational number. It is known as Euler's number. That's pronounced Euler, not Euler. Known as Euler's number, and it is an irrational number. It has a decimal that goes on forever and ever and ever. Here is an approximation of e. In case anyone's curious, I had a lot of fun doing this before class. E, like pi, goes on forever and ever and ever to the right of the decimal place. So I am not allowed to say that this is e up here, because no matter how many I have here, and I think this is roughly 1,000 digits, I found this online, roughly 1,000 digits, it keeps going. So you'll notice at the very top here, I didn't say e equals this, I said e is approximately equal to this. Now, of course, this is a very awesome approximation of it, but it is still just an approximation. Just like if you go to one of those weird parties and someone's saying, I'm going to do pi, and they're like 3.1, I don't know what goes after that. But they start doing pi, no matter how far they go, are they still just giving an approximation? Yeah. So this is a very special number that we learn about in this section, but there's one thing I want you to notice about this number. First of all, for the sake of not making ourselves sick, I'm just going to write it like that for the moment. It's approximately equal to 2.718. But I do notice that 2.718 is a positive number. And if it's a positive number, what am I allowed to use it as?
It's a base.
I can use it as a base. And it is not uncommon to hear people call this the exponential function. People get so giddy about this thing, they call this thing the exponential function. Not just any exponential function, but the exponential function. And why does it work? Because even though it's a long, horrible decimal, it follows the criteria to be a base. It is a positive number not equal to 1. What does its graph look like? It looks something like this. Why? Because the graphs all look like that if it's a positive base, not equal to 1. It grows a little faster than y equals 2 to the x, and a little slower than y equals 3 to the x, because e is in between 2 and 3. But what should really tick you off at this point is that pi comes from somewhere. Pi is the circumference of a circle divided by its diameter. That's where pi comes from. So where in the world does e come from? So we'll call this next part of the lecture Math Origins. E. Were they doing that for a while? Like X-Men Origins, Wolverine, or Thundercats Origins, Panthro? Okay. So, here's where E comes from. And you might not like this, but this is where it comes from. You take the rather complicated looking equation, or I'm sorry, expression, 1 plus 1 over x to the x power. You don't need to write this down, everyone. You can if you want to, but I'll post it later. 1 plus 1 over x. And then what you do is you let x approach infinity. And what I mean is, you first let x be a 10, then 100, then 1,000, and you plug these numbers in here. So you end up doing 1 plus 1 over 10 to the 10th. And what's going to happen here, as you do this, everyone, is what you're going to be doing is you're going to be taking bases just barely larger than 1 to very large powers. Because what you're doing is you're adding a fraction that's not very big at all, like 1 over 1,000,000 to 1, and that's going to be a very, very good number very close to 1, and you're taking it to these enormous powers. And what happens is, the higher that number gets, in other words, as we approach infinity, the answer, the decimal approximation over here, gets very, very close to e. That's actually where it comes from, everyone. Or, and this one's actually a little bit, I actually like this one a little bit better. Where's origin story part 2? Oh, here it is. Here's another way you can approximate e, everyone. This one I actually like a little bit better. What you do is you start adding up a bunch of fractions together, like this. And the way where you get these fractions from is the next fraction always comes from multiplying the denominator by the next number. So everyone look at this. What's 1 times 1? Times 2?
2,
Times 3?
6,
Times 4? 24 times 5, 120, times 6, 720, times 7, 5,040. And if you do this forever and ever and ever, this will go to e also. To the next fraction, you multiply the denominator by the next counting number. So that's kind of where e comes from. So this class really doesn't focus on where e comes from very much, but I wasn't going to throw this new fancy number up here and say, here it is, enjoy, good luck. But what it does focus on is what e is for. And it's such an important base to us that it actually turns out as you move on in mathematics, it's going to be the base you use the most. But don't let it freak you out, everyone. Don't let it freak you out. What's e to the 0th power? 1. What's e to the 1st power? E. What's e to the -1 power? 1 over e. On your calculator, you should probably see a button that looks like this. You might have to use the second feature to do this. It might be above a button. And the reason it looks like this is because we almost always take e to a power. That's why it doesn't just say, that's why it's not just an e button, it's an e to the x button, because it's going to assume you want to take it to a power. But everyone, if you do it on your calculator and you do it to the 1st power, if you push the button 1 after you push that and then push equals, you will get that approximation for e on your screen. It'll show up on there. All right. We will get back to why e is more important here. After one more example, then we'll go back and double back to e. But for right now, what I want you to know is it's not our enemy. It's a number that's approximately equal to 2.7. It's a valid base because it's a positive number. And it does mathematically come from somewhere. I can't explain it as easily as saying circumference divided by diameter equals pi, but it does come from somewhere. E will return after these messages. Okay. What are exponential functions good for? The first application we learn is compound interest. Exponential functions are used to find compound interest. In other words, yes. We put money into a savings account and earn interest on our principal investment, as we earn interest, we earn interest on our interest. And that explanation is why I'm not an economics teacher. Compound interest just means as your money gets bigger in your account, you start earning more money because you got more money in there. All right. For those of you that hate story problems, you're not going to like this. For those of you that always want to know what is this going to be used for, you'll like this. This is how we figure out interest. And what happens, everyone, is we have a variable up in the power. That's why this is considered an exponential function. You have a t right here, and there's a t up here in the power. That's why this is considered an exponential function. That's why we learn about it in this section. To use this formula right here, you need to know the principal, the starting amount, the present value, the amount you begin with. You need to know where you start. You need to know your interest rate as a decimal. In order to use this formula, you need to be able to convert an interest rate that's given as a percent into a decimal. Otherwise, this formula doesn't work. You need to know time in years. This particular equation, this particular formula is designed to have time be in years, not months or days or weeks or anything. You can adjust it to make it for one of those, but this one is designed for years. N, which shows up twice in the formula, once below the r and once multiplying by the t up in the exponent, is compounding periods per year. And what that means is how often interest is added back into your account so you can earn interest on interest. Yeah, I know, everyone. I know. Principal, the starting amount, R, the interest rate, T times years, and N is how many times it gets compounded per year. Now, the way you figure out N is just by reading a story problem. And you'll see something written in the story problem like this. Yearly. And that would tell you that N equals 1. Or you'll see something like this. Monthly. And that would tell you that N equals 12. Or you'll see quarterly. And that would tell you that N equals 4. Or you'll see daily. And that would tell you that we assume it's not leap year and N equals 365. So you'll see something written in the story problem that tells you what N is. You just need to translate that word into a number. A is our ending or future amount. How much we have it when it's all done. How much we have when everything is over. So I'm going to show you how to use this formula right now. The good news is, once upon a time, the powers that be decided that we're allowed to give you this formula on the test. You don't need to memorize this formula. You do need to learn how to use it. But the formula, A equals, oops, maybe I need to memorize it. A equals P, 1 plus R over N to the NT power is given on the exam. Not the explanation of how to use it, but that will be given on the exam. And here's how we use it, everyone. How much money do we have in total if we invest $5,000 at 4.5% interest, compounded monthly for 8 years. This is what a question might look like, an interest question might look like. How much money do we have in total if we invest $5,000 at 4.5% interest compounded monthly for 8 years? All the information we need is right there. We just need to remember what each one of these letters stands for. Class, what does capital P mean? Or what number is capital P? The starting amount. How much should we start with? $5,000. 1 is just 1. What's our R going to be? Interest rate, and you're right, it's going to be 0.045. Because we have to convert it to a decimal. Now, to go, remember, just go percent to decimal. Percent to decimal, move point 2 places left. You just move it 2 places to the left, and you'll get it. What's n going to be? How many times is compounded? So what's the number going to be? 12, because we said monthly. This right here, monthly, that's telling me my n value. Oops. So that's going to be 12. And the power up here is going to have that 12 again, because n shows up twice in the formula, and it's going to be multiplied by what number up there?
8.
8 years. Now, absolutely, you do need some practice to plug this into a calculator. So if you want to join me, I will tell you what I think is the safest way to do this. I get the power first. I multiply the two numbers up in the exponent together, and I get my power first. And I write that off to one side. I clear my calculator after I get that 96. I just walk away for a moment. Then what I do is I would do the 0.045 divided by 12. I hit equals. Then I would do plus 1, and I hit equals again. Then I would take whatever that result is, to the 96 power. You take that result, whatever you just got when you did the inside there, you take that to the 96 power. And even though it's the first thing written up here, it's actually the last thing you do. Last. Multiply by 5,000 and round to 2 decimal places, which just means the nearest penny. This is a math problem, so we round to the nearest penny. Or you could write some secret program that makes it so all the fractions of pennies go into a secret account for you. They tried that in Superman 3. Okay. If you do this, who's feeling confident they got a good answer?
7,161.82.
Do I have a second on that from someone? Second, third? Good. That's how much we have. Because what did the question ask? It asked, how much money do we have in total? What if the question said this? How much do we earn in interest? What would you do? Subtract the 5,000. That's exactly what you do. Now, class, there's not much point in me doing a dozen examples like this, because this is really just something you have to practice on your own. But this is how you do an interest problem. So you look for the important pieces of information, the amount you start with, the interest rate, how often it's compounded, and how long you keep it in there, and you use this formula. Do not try to memorize this formula, you don't need to, but you do need to learn how to use it. And more than that, you need to not only know how to set it up, but you have to know the proper order to plug it in your calculator. And if you were trying to do this along with me today, or you're trying to do this by yourself later and you're not getting this, come see me so I can help you with your calculator. I'd be happy to. Finally, there is one time with interest problems where we do not use this formula. If interest is compounded continuously, that means that n is approaching infinity. N is approaching infinity. Because 1 plus 1 over n to the nth approaches e as n approaches infinity. And there's a little bit more to it than that, but that becomes a calculus problem. If you see continuous you use this formula instead. If it says the interest is compounded continuously, that means you use this formula instead. It is a different formula. In other words, class, you are going, yeah, some people do call it the PERT formula. You are going to use this formula right here on the left if you see quarterly, monthly, yearly, daily, all of those things. But if you see continuously, you use this formula instead. That's the one time you use it. Otherwise, you're over here with this one. So when someone says to you, $4,000 is invested at 3% interest, compounded, I still have 2 minutes, continuously for 20 years, how much do we have in total? As soon as you see this word continuously show up, you are using what some people call the PERT formula, which I do not have time to do today, but I will show you that it gets set up like this. But I am, unfortunately, out of time, so we'll have to pick it up again here next time. Everyone, thank you so much for coming. I hope you learned a lot, and we will